I will get started. Ahem. 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 All right. I will begin with a word of prayer. Dear Father, we thank you for this day. Again, I thank you for the students. Just ask you to bless our work today. Help us to glorify you, what we do, Lord. In your name I pray, Lord Jesus. Amen. Amen. All right. So I have an example to return to. Let us begin. Example 1. Suppose you have a parallel inductor circuit like so. We'll close it at time 0. Resistance here. You got one inductor here. You got another one over here. All right. Voltage source E. This is going to be R. This is going to be L1. This is going to be L2. All right. And then I'm going to label the currents like I did last time. So we'll call this current 3 up here. Current 1 goes this away. Current 2 goes that away. All right. And so I just would point out we have a few different relations, right? Number 1, I have that the voltage minus I3 times R minus L1 di1 dt. Well, that's equal to 0. I wrote that one down last class, but we also have that E minus I3 R minus L2 di2 dt is equal to 0. It didn't seem like that would be helpful, but actually it's pretty helpful to write that down. 3, of course we have conservation of the currents, like I2, I1 plus I2 is equal to I3. We have that. And 4, we also have that L1 di1 dt is equal to L2 di2 dt, right? So we got all these equations floating about. One of the first things I did as I solved this later, away from the corrupting influence of CFAW visitors, is I differentiated equation 3 and solved it for di1. So like di1 dt is equal to di3 dt minus di2 dt. I'm going to label that equation 5. All right. So to solve these, using the method of substitution, I begin by substituting 5 into 1. All right, so let's substitute 5 into 1, see what that gets us. So substituting 5 into 1 gives me E minus I3R minus L1 times, parentheses here, di3 dt minus di2 dt equals to 0. I label this equation 6. All right, so this is 6. Here's equation 6. Next move. From 2, we deduce the following, right? What do we get from 2? From 2, see that di2 dt, we can solve for di2 dt equal to E minus I3R divided by L2. Thus, by 6, we obtain that E minus I3R, let's see here, minus L1, some parentheses, we got ourselves a di3 dt minus 1 over L2, parentheses, E minus I3R. I'll close these bigger parentheses like that, equals to 0. I'm going to call that equation 7. And this is what I was after last time, but I could not get. Right? I could not see my way to this last class. I had many of the ingredients that were needed to get to it, but just not quite everything, right? I think missing equation 2 was probably the most damaging thing last class. That was probably the thing that was actually keeping us from it. Okay, now once we have this, we want to clean it up. So to clean this up, clean equation 7 up, I'm going to rewrite this as L1 di3 dt, all right? Let's see here. Plus I3R times what? Well, let's look at it. So I just moved that. Basically, I just moved this term to the other side. All right. So I'm moving things to the other side. So I got like a plus on the L1 di3d term. So the other terms that have I3R, like this one, and also that one, it's going to give me a, let's see here, 1. And then, oh, notice there's 3 minuses. 1, 2, 3. So it becomes a plus on the other side, plus L1 divided by L2. All right, that's all my I3 terms. That's going to be equal to, let's see here, I've got E times 1 plus L1 over L2. Right? Now, the way we solve these is to isolate the derivative. So I want to divide by L1 now. So dividing by L1, I get what? I get di3 dt plus, you know, I'm going to write the I3 second this time. So I've got like 1 over L1 plus 1 over L2 times R times I3 is equal to E times 1 over L1 plus 1 over L2. All right? And then at this point, I'm going to make a definition, right? I'm going to say, oh, okay, let's let L equals to 1 over L1 plus 1 over L2, right? If I make that substitution, then I can rewrite this as di3 dt plus R over L I3 equals to E over L. At which point, we're home free, because that is the RL, that's the RL circuit equation that we had at the start of like the class before last, right? Remember, that's the equation for the RL circuit. This is the equation we get if we just have like, you know, a voltage source E with a resistor R and an inductor L. So this parallel circuit is equivalent to this circuit right here, with the equivalent inductance being defined just as we expected. The reciprocal of the sum of the reciprocals, which of course you could rewrite with the usual formula, right? L1, L2 over L1 plus L2, you know? Also true. So let's solve. So with that said, let's solve this thing. What's the solution then? So let us solve di3 dt plus r over L I3 equal to E over L, given I3 of 0 equals to what? What is this class by ours? Like, and why can't they shut up? Like, what is it? Do you guys know? I should go over. Should I go over and find out? Should find out. Should be fun. I used to have like linear algebra next to a German film class. It was really odd. Sometimes the professor would stop and listen because he understood German. But anyway. Okay, anyway, so usual song and dance. We multiply by e to the t over tau, di3 dt plus r over L e to the t over tau, I3 equals, you know, e to the t over tau, e over L, where what's our tau equal to? Time constant defined to be L divided by R. All right. So with that little integrating factor multiplying, we have ddt of you know, e to the t over tau times I3 equals to e over L e to the t over tau. Integrate both sides, and we get I3 times e to the t over tau is equal to, well, tau times e over L times e to the t over tau plus a constant, I suppose, if you like. But I3 of 0 equals to 0 implies that that constant has to be equal to minus epsilon tau over L, which of course we could simplify, right? That's minus epsilon L over LR, which is just minus epsilon over R. So lo and behold, the current through the current through the resistor, I is function t, is just equal to E over R times 1 minus e to the t over tau. And there's a minus here, if I did it right. Because I have to solve, I have to multiply by the, I have to divide by the e to the t over tau, which ends up putting the, cancels these two exponentials out and just leaves me with 1 on the constant, which gives me that. Anyway, of course, another viewpoint here is you could just go back to the example we did 2 classes ago and just plug in the equivalent inductance in the solution that we already derived, right? I'm just going through the steps we already went through, you know, calculus-wise. So there it is. Now question. So I have some questions. Like, what is the current that flows through L1 long term? Can you answer that? No. Now you're right. That's the current that flows through through I3. You know, that's true. But that current gets divided between the inductors. How does that happen? So we can derive that now. Let's derive it. So like, what's I2? What's I1? Can we figure it out? We got a bunch of equations to use, you know. Which one's the right one? How about this one? See, di2 dt is that. So let's go back to that guy. We had di2 dt is equal to e, I'll write it this way, 1 over L2 times e minus I3R, which is what? 1 over L2 times e minus, like, e times parentheses 1 minus e to the minus t over tau. The r's, they be canceling. The e's, they're canceling. So what we have is di2 dt is equal to apparently 1 over L2 e to the minus t over tau. Right? And I think we should integrate this time. So let's try integration. So let's integrate di2. I'm going to change the t to a t-bar. dt bar from 0 to t. And that's going to be equal to the integral from 0 to t of 1 over, I mean, we could fit constants again, but I'm bored of the fitting constants. So I'm going to do the calculus a different way this time in the hope that I might confuse some students. You know, after all, that's my goal. Yeah. Oh, yes, thank you. I'm clearly not confusing the students enough. You can still see that. It's not good. I got to try harder. So on the right-hand side, we have I2 of t minus I2 of 0. On the left-hand side. On the right-hand side, we have, minus epsilon tau divided by L2 e to the minus t bar over tau evaluated from 0 to t. Which is, let's see here, epsilon tau over L2 times 1 minus e to the minus t over tau. Consequently, I2 of t is equal to, let's see here, my tau was epsilon, what is epsilon? Let me write down this mysterious epsilon tau over L term. What does that actually mean? We got what? Epsilon tau over L2, which is epsilon, tau was what? It was L over R, right? But that is epsilon L1, L2 divided by R times L1 plus L2, right? And there's an L2 downstairs. So that actually simplifies simply to epsilon L1, the L2s, they be canceling, R times L1 plus L2. So I get epsilon L1 divided by R times L1 plus L2, all times 1 minus e to the minus t over tau. There you go. That's the current as a function of time through the second inductor. Once you know that, finding the current through the first inductor is pretty easy, right? Because we can just solve the current equation for the other one. I'll give you guys a second to catch up before I do that, though. Any questions? Yeah. So, yes, it's on the test. Anyway, go on. Yes.
But for every RLC circuit, will we have to do like the thing on the left?
For every RLC circuit, do we have to do the thing on the left?
Or is it, because you see the bottom on the red, that equation?
This here?
Yes. Just memorize that.
Well, my goal in all these problems is to, like, when I have more currents than one, I want to find an equation which just involves one current, because then I can just do calculus 2 on it. If I have two currents, then it's still still like conjoined. It's still intertwangled. I can't solve one without solving the other. I have to solve them both at once, right? So I have to isolate. That's the goal. And then the other thing is just like format-wise, I remember that that's what the equation was that we had with the charging inductor, like the charging inductor problem basically was exactly that equation. We went from there to this solution, doing this same calculus but with slightly different letters. But yeah. And I'm introducing the time constant early on because it makes the calculus easier to follow. Otherwise, we'd be writing R and L 20 times. But instead we're just writing tau, which is actually kind of more physically interesting anyway. So once we have that, what's I1? So it would be what? I3 of t, right? Minus I2 of t, is that right? Yeah, I3 minus I2, which is equal to, so you got yourself an E over R times 1 minus e to the minus t over tau, right? Minus E L1 over R times L1 plus L2 times parentheses 1 minus e to the minus t over tau. And if you tilt your head and squint, you got an E over R. I'll factor that out. And we're going to have a 1 minus L1 over L1 plus L2, right? Sorry, I'm too close to it. I guess I can write it out as a separate thing, but well, minus, fine, I'll write it out again. Minus E over R times 1 plus, well, not plus, but minus. It's the same thing, both terms. I mean, however you want to do the algebra here, L1 plus L2. E to the minus t over tau, I believe. Let me step away from it. I stepped too far. No, I can't see it. Gotta squint. There are 4 terms. Yeah, I think that's okay. So notice what happens is if you do the math here, this is just what? E L2 divided by L1 plus L2 times parentheses 1 minus e to the minus t over tau. If you simplify this, see they're both the same. They're both the same expression there. I lost my R. R. Thank you, thank you. Let's put that back. That belongs. Right. So let me ask the question again. What's the current that flows through, like, the first inductor as time goes to infinity? So you can see it from here, right? As t goes to infinity, I1 goes to what? So the time constant term drops out, and you're just left with, you know, E L2 over L1 plus L2 times R, right? And on the other hand, I2 goes to E L1 over L1 plus L2. You know, if we were smarter, I mean me, you guys are smarter, then you would have just told me, well, if we did 1, we've already done 2 because these expressions are completely symmetrical. So surely the formula for 2 must be the same as the formula for 1, just switching 1 and 2, right? And you would have been completely within your right to make that argument, you know? But we did show that the algebra works out just the same. The algebra bears out the symmetry argument, which is good. But this is the deal. So we have basically L2 over L1 plus L2, that's the fraction that goes through I1. And L1 over L1 plus L2, that's the fraction that goes through I2. And of course, E over R goes through the both of them combined. For instance, if the inductors are equal, half the current goes through one, half the current goes through the other. If the one inductor was like 3 henries and the other one was like 1 henry, I think more current goes through the lower inductance, right? Like the current will go through the lower inductance more, I think. Wait a minute. No, other way around, right?
Wouldn't that because I1 is based
Oh, yeah. I can't read my own formulas. Yes, thank you. Yeah. Any questions? So what's the long and short of it is that equivalent inductors, in fact, do work exactly like equivalent resistors. That's the long and short of this. So let's do a super easy example that's born of this example. Like example 2, suppose you've got the following circuit. You've got 1 millihenry, and then you've got let's say 10 millihenries here, 10 millihenries here, right? And then you've got, oh, I don't know, let me just pick a random number, 41 millihenries, like that. This is equivalent to what? You got your 1 millihenry. These are the same as what? 5. And you got, these are in series. What did we learn last time? Series just add, right? So this is equivalent to the single inductor of 1 plus 5, 6 plus 41, 47 millihenries. An interesting number, I think. Something relevant. Something about 47 is interesting. What is it? I don't know. Something interesting about 47. Sorry, I'll stop eventually. But not today. Any questions? So we could also ask follow-up questions like how much energy is stored in each inductor now, right? As a function of time, we could easily figure it out, right? Because like the energy stored would be what, 1/2 Li squared? So like the energy stored in I2 at any time would just be 1/2 Li2 squared. The energy stored in in the first inductor, 1/2 L1 I1 squared, right? Yeah. Okay, so there's that. So sorry I got stuck last time, but at least I was trying to do the right thing. And I didn't make a mistake, I just got stuck. So. You're like, that's not going to stop you from taking points off of my next test when that happens to me. That's true. It's a fair appraisal. But the only way I have to get points is to take them from you, so what else am I going to do? You know? Let's see here. I can't take them from like Dr. Badara's. He won't give them to me. All right. Let's see here. Let us discuss the RLC circuit a bit. All right, so the RLC circuit's what it sounds like. Suppose you've got, you know, a resistor, an inductor, and a capacitor, okay? And that might be all you have, right? And then you could do something like you charge, you know, initially charge the capacitor up with charge Q0, right? And then you close the switch at t equals to 0 and see what happens, you know? So what equations does such a circuit have to solve, right? So we put everything we've done so far together, and we get the Kirchhoff's voltage law of L di dt, right? Plus I times R plus Q over C is equal to 0. So this is Kirchhoff's voltage law. You know, this is how the voltage behaves. Ohm's law for the resistor, you know, essentially Faraday's law paired with our definition of inductance for the inductor. And this is essentially the definition of capacitance, right? Okay, but what is this? Well, since, you know, I is equal to dq dt in this context, we have, what do we have? We have L d squared q dt squared plus R dq dt plus q over c is equal to 0. All right? Which I'll rewrite it a little bit. This can be rewritten as d squared q dt squared plus R over L dq dt plus 1 over LC q is equal to 0. So let me give you a very short tour of the mathematics here. Like, what happens? How do you solve this? The way this kind of equation is solved is you basically assume that you can solve it with an exponential. All right? So if we plug an exponential into this equation, what's it look like? Like, suppose q of t is equal to like e to the lambda t, where lambda is just some like unknown quantity we're trying to, you know, use to form our solution with this lambda. You might sometimes in the differential equations class, you guys might use e to the rt, but I don't want to use e to the rt because r is easier for the students to understand, and I think lambda confuses the students more, so as such I have to use lambda. But sorry, I'm an idiot. But you already know that. So if I differentiate 2 times, well, first of all, what's dq dt? I get lambda e to the lambda t, right? And if I differentiate a second time, I get lambda squared e to the lambda t from the chain rule. So you take these, right? You take these and you plug them in up there, and what you get is lambda squared e to the lambda t plus R over L lambda e to the lambda t plus 1 over LC e to the lambda t equals to 0 if it's going to work. Like, that's what we need. So this right here is an educated guess, all right? It's a much more educated guess if you've already had differential equations. Some of you, well, most of you have not, right? Anybody in here diffie-q? Like, oh, few. So you guys are bored at the moment, right? At the same time, no. I mean, like, I don't test on this in differential equations because physics 2 is frightening to much of the audience there, so I don't try to intimidate them. But it's really not bad. Look, this is
You really do love the math majors more.
lambda squared. I do love the math majors more. Yeah, I guess you got me. It's true. Lambda. I love all the majors. Well, that's not true. But yeah, fair enough. Yeah. But I don't hate engineering. I think engineering is a good major. It's a solid major. It has its virtues. I don't find it to be morally objectionable or anything, for sure. Not like some majors. I won't say which ones. But there you go. Most of those majors we don't have here. Anyway, so in order for that to work, we need that the quadratic equation in lambda has to be 0, right? That's the deal. The quadratic equation in lambda has to be 0 there. And so you know the drill. So lambda is equal to what? Like, you know, minus r over L plus or minus the square root of r over L squared minus 4 times 1 over LC, all right, divided by 2. This is the quadratic equation, right? And so essentially, you can look at the quantity. Maybe we can clean up the thing under the square root. Under the square root, we have what? R over L squared minus 4 divided by LC. So let's see here. This is actually what? R squared times C minus 4 divided by what? Oh, 4, I should put a 4LC over here. 4LC, right? Over L squared C squared. What should I make for my common denominator here? Maybe L squared C, maybe that's good, right?
It should just be 4L on the right, not 4LC, right? Give an LC on the denominator of that one.
Okay, so just 4L? Do you guys agree, disagree? I mean, this algebra is not like hardwired into me or anything. I'm trying to work it out. My point is that that's the thing that goes into the square root. That's the discriminant of the quadratic equation. So notice that we could just focus on R squared C minus 4L determines the sign, right? You know, I don't want to write it again. Let me just give this thing a name. Bob. Right? So depending on whether that's positive or 0 or negative, you get different kinds of solutions. So like, if we had R squared C minus 4L is positive, that would imply that your solution was like Q, had the form like Q, let's say C1, C1 e to the, I'll say lambda minus t plus C2 e to the lambda plus t, where I'm saying plus and minus are the solutions that you get from the plus and minus up there, all right? That would be if it's positive. Now if it's equal to 0, that would say that the charge as a function of time is something like C1 e to the lambda t plus C2 t e to the lambda t. And finally, if this R squared C minus 4L was less than 0, that would give us charge that has the formula something like Q naught e to the alpha t, let's say cosine of beta t plus a phase angle. So all of those behaviors are possible depending on how the resistor and the inductor and the capacitor are related. The reason for this is that this is the same, physically speaking, as a spring mass system under friction, right? So like the spring mass problem corresponding to this is when you have the mass times the acceleration is equal to the spring force minus the the friction force here, like that. And so that gives you like a m x prime prime plus bx prime. If I divide by m, I have mx prime prime plus b over m x prime plus k over m x equals to 0. So this equation right here, you can make a direct physical analogy to the RLC circuit. And the analogy is this, which is that, well, rats. I should have done this one. Let me do this. This one's easier. So let me write it right here. So I have a mx prime prime plus bx prime plus kx, right? So this is the corresponding physics 1 equation. The analog is that the mass is like inductance, right? The resistance is like the coefficient of friction, and the spring constant, oh man, I seem to have switched my analogy. B is like resistance, and the spring constant is like the reciprocal of capacitance. So anything you can say about the spring mass problem under friction, there's a corresponding thing you can say about the RLC circuit and vice versa. They share the same mathematics, and that's why we spend a fair amount of time in differential equations trying to really understand this structure as deeply as we can. So Now here, we could study the energy stored in the capacitor at any time, right? What would that energy be? How would we find the energy in the capacitor at any time in this problem? We do what? Like Q squared over 2C would be the energy stored in the capacitor, right? To find the energy stored in the inductor, we'd have to look at 1/2 Li squared, right? And what we should see is that the energy in the capacitor and the energy in the inductor, they go to 0 after a long time because the resistor is always just eating up energy through dissipate, through power basically. It's I mean, not thermal outlet, right? I squared R is the power developed in the resistor. So anyway, I don't, this is mostly informational. I don't expect that you're going to learn how to solve. Like, I'm not holding you guys to these solutions. You're not expected to memorize them or apply them. The only one I want you to know is the LC circuit. That I do want you to know. That one I expect you to be able to do. That one's much simpler. There's no, it's just the sine thing we looked at the other day. We worked that out separately. So that one I think you should know. LC circuit, you should know. But the RLC, I might give you in the homework. But I don't usually test it because I need to spend another 30 minutes to properly teach you these solution techniques, right? There's not much to learn here. I've taught, like when I taught calculus at NC State to start with as a grad student, this is part of the Calculus 2 course. In NC State, in Calculus 2, we teach second order constant coefficient differential equations as part of Calculus 2 because engineering wants us to at NC State. Because they want their engineering students to know that early on. But I've yet to receive such a request from your professors. But if I did, rest assured it would be taught in Calc 2. But anyway. Okay, so just to give you a snapshot of where we are, where we're going, I do need to still spend some time talking about mutual inductance a bit. So I'll try to talk about that, what that is, and give you an example of it maybe next class. And then we need to talk about the Maxwell's correction to Ampere's law, I believe it was. So anyway, I think that's a good place to stop for today. The rest of the time, why don't you guys talk amongst yourselves, talk to your groups, make sure everything's in order. Right? You all have a group. If you don't have a group, you should be part of a group. Let me stop the thing here.